Okay, the goal of this one is I realize that sometimes in doing calculations in the Collaborate sessions and various other places, that I tend to do the algebra quite speedily and sometimes skip steps and so on, just in the interests of space and time. But which is, a good physics reason to do things. But I know that it might be a while since you've done algebra at these kind of levels, and that maybe it'll be useful to just have a little bit of a refresher on some of the tools and tips and tricks. The absolute key to this stuff is the equal sign, and specifically ensuring that whatever is on one side of the equal sign is equal to and stays equal to whatever is on the other side. So basically the bottom line is do to one side what you do to the other. And that sounds potentially insultingly simple, but I'll give you a couple of quick examples just to make sure that we do it. And again, if you're struggling with the algebra, use more lines, do it more slowly, don't skip steps, don't do steps in your head, and so on. So let's do a really simple equation. X plus 3 equals 7. Right? Yeah, insultingly simple, but whatever I want to do to one side I have to do to the other. So I want to get rid of this plus 3 to get the x by itself as the subject, so I will do minus 3 to this side so that that will cancel out. But whatever I do to one side I have to do to the other, so I'll do minus 3 to this side. So that will just end up being x equals 4, and I've solved that. Now, so quite often what we're trying to do is solve for the value usually of one variable, and we need to make sure that, again, whatever is at one side of the equation is the same as what's at the other side, that the equal sign is true, in other words, that what's on one side is matches what's on the other side. So here's another example, if I can get the thing to move. So if I go, let's see, x squared equals, no, I'll do it slightly differently just for fun. X squared minus 8 equals 1. Okay, so first step is going to be the same. I'm going to add 8 to both sides because I have to cancel out this. So for a minus 8 we need a plus 8, and to do the same to both sides of the equation. So I'm going to get x squared equals 9. But often what people will do is just go, okay, I know that the right hand side is equals 9, and then I will do the square root. Square root of 9 is 3, and so I'll just do equals 3, but that's not x squared anymore. It was x squared here, but it's x here. So you've actually changed what's on one side of the equation without changing what's on the other. And you'll see that quite often as a mistake in calculations. So again, these two have been kind of very simple, but hopefully useful. So let's just try and use these tools to do something a bit more complicated. There's an expression for the period of a pendulum, which is t equals 2 pi square root L over G. Now let's say that what I want to find is the value of G from this equation. So that means I need to get G as the subject. G's under here. I need to get it as the subject of the equation. So what do I have to do to get G by itself on the left-hand side as the subject? I reckon because it's under a square root, and that's messy and ugly and makes life difficult, I'm going to square everything. Square everything on both sides. So squaring the left-hand side is relatively easy, t squared. But I have to square this as well, so 2 squared is 4. Pi squared is just pi squared. Remember, pi is just a number. Don't be scared of it. It's not a pronumeral. It's just a number. 3.14159 is probably accurate enough for our purposes, but we could keep going forever. And then what we've actually done is multiply square root of L over G times square root of L over G. In other words, that's what we do when we square it, and that just gets rid of the square root sign and makes it just L over G. So we get rid of that, and we get rid of that. So we've rearranged it so that we have t squared equals 4 pi squared L over G. We've got rid of that inconvenient square root. We could also write this as 4 pi squared L over G if we wanted to. There are conventions, and with fractions, because you're multiplying by the fraction, you can move it around like that. There are things like often we'll put, so let me write it over here, instead of say cos 30 t, we'll typically write it as t cos 30. So if you see me in mid-equation rearrange those kind of things, multiplication, the order doesn't matter. The mathematicians among you know that there's a term, it might be commutative, but don't quote me on that. As with English, I know how to write a very coherent sentence, but I don't know always which is the adverb and which is the adjective. With maths, I know how to do it. I don't always know the technical language of how to describe it. Okay, but we're not finished yet because we want G as the subject. So now in this case, we've divided by G, so we want to multiply by G because that's going to cancel out as well. So if I put G there, then those two will cancel. But again, whatever we do to one side, we have to do to the other side. So we multiply the other side by G as well. So we have GT squared. Just get rid of the messiness. GT squared equals 4 pi squared L. We still don't have G by itself, which is what we're looking for. We want it to be the subject. We want it to be the only thing on the left. So now we have to divide both sides by T squared. Oops. Let me try that again because I turned the dividing line in the fraction into the top of the T. T squared, and again, T squared will cancel T squared, but if we divide the left by T squared, we also have to divide the right by T squared. So that rearrangement of that formula ends up with G as the subject. G equals 4 pi squared L over T squared. Now we can't cancel anything else out there. The fact that you've got a pi squared and a t squared is not particularly helpful because they're different things. But that's the final expression of, we've taken that expression which started out as having the period of the motion as the subject and made the acceleration due to gravity the subject instead. I probably should have pointed that out actually. This is period in seconds and this is length in meters and acceleration in meters per second squared. We could actually also go through and work on the units and make sure that they're consistent as well. Pi being a number has no units. But let's maybe just do one more example of a rearrangement like that. Let me think of a good example. This is one that we've seen quite a bit. One of the equations of motion that we use is v squared equals u squared plus 2as. So let's say for a start that I want to make s the subject. I'm interested in the distance travelled, and we use this a couple of times. We'll used it a large number of times. I'm thinking of it because we used it in some of the projectile motion problems that are in the week 5 Collaborate session that I'm about to do in about 20 minutes from now. But we've used it quite a few times. So what am I going to do? I want to get S as the subject. So I need to, let's just actually flip the whole thing. So I'll just write it in the reverse order. And again, we can completely do that. 2as plus u squared. I haven't changed anything yet. I haven't moved anything to the other side of the equal sign. I've just flipped right for left. And if it's equal, it shouldn't matter, right? The two things on each side are equal, so it doesn't matter where you put them. Now, all right, first step, I'm going to subtract u squared from both sides. I want to get rid of that u squared because it's messy and I don't like it, or I don't like it where it is at least. So a plus u squared and a minus u squared will cancel out, and we'll have 2as equals v squared minus u squared. Okay, now I haven't finished yet. We want s to be the subject, so we can divide by, we could do it in 2 steps and divide by 2 and then divide by a, but let's just divide both sides by 2a. So we'll divide that side by 2a and those will cancel out, and we'll divide that side by 2a, and we're done. just rewrite it neatly. S equals v squared minus u squared over 2a. So that wasn't too difficult, just the same stuff, doing the same thing to both sides. Let's say, though, that I make life a little bit more difficult, and decide that I want u as the subject instead. Now I'm going to start with the same equation, but I want u as the subject. So I'll start again with v squared equals u squared plus 2as. What will I do? I think I'll flip it again because I want that u squared to be over on the left. So u squared plus 2as equals v squared. Now I'm going to subtract 2as from both sides because I'm trying to get the u by itself. Minus 2as. So I've got u squared equals v squared. Whoops, that's not a v. Equals v squared minus 2as. And now, because I've got a u squared, I want to take the square root of both sides. I want to take the square root of u is going to give me, so if I take the square root of this side, I get square root of u squared, which is just u. If I take the square root of this side, I can't actually do much more than just write it as square root of v squared minus 2as. Because there's a sum there, I can't actually go square root of that minus square root of that. Because if you think about it, let's actually just do an example to make sure that we're comfortable with that. So let's say I've got v is 2. Let's say I've got 2 squared minus 3 squared, the square root thereof, and this is going to require some calculator, equals the square root of, oh no, that's nasty. That's going to get into imaginary numbers. Let's not do that. Let's go 2 squared plus 3 squared. So 4 plus 9 equals square root of 13 equals... That was me grabbing my calculator from the other desk. It equals about 3.6. But if instead I go square root of 2 squared plus square root of 3 squared, I get square root of 4 plus square root of 9 equals 2 plus 3 equals 5. So you can see that that and that are not the same thing. So in this case, we can't go square root of v squared minus square root of 2as. We have to go square root of v squared minus 2as. All right, we can talk a bit more about this, but really it is just practice. It's figuring out, it's not getting scared of squares and square roots, or even cubes and cube roots if we run into any. It's not getting scared of pies and thetas. It's not getting scared of causes and sines. And maybe we should, no, actually what I'm going to do is do another video, which is an introduction to trigonometry, and we'll get into sine, cos and tan, where they come from, how we can use them in right angle triangles, and how we can use them in non-right angle triangles. But that's for a different video. Hopefully this has been a bit of a refresher on the things that we're doing when we're doing some quick and easy algebra in this physics, in the service of physics. Thanks a lot.